Today it is my pleasure to present Professor Caroline Nore. She's a professor at University of Paris Saclay and LIMSI laboratory at Orsay. He's a professor there from 2007 to present, and from 2000 to 2002, she was a research scientist at CNRS in France. From 1996 to 2007, she was an assistant professor at the University of Paris in Orsay, France. Well, thank you very much, Professor Nore, for your talk in our seminar, and please go ahead with the presentation.
Thank you very much for the invitation, and thank you for the presentation also. And as you said, so I'm professor at Université Paris-Saclay, and the study I will be presented today is about mixing in liquid metal batteries. And this study was made in collaboration with Wietse Herman, Pedro Zibel Ramos, and Sabrina Benard from my lab, and also with Loïc Capanera from University of Houston in the United States, together with Jean-Luc Guermont from Texas A&M University, and Paolo Personetas and Norbert Weber from LGDR. And so we are interesting, we perform some numerical studies about mixing in liquid metal batteries. And you all know, oops, it doesn't seem to work, sorry. Here, yes. Do you see my slide now with the liquid metal batteries?
Yes.
Schematic of it? Yes. And so we want to store, in fact, intermittent energy using this kind of device. And so just to present it, so you have 3 liquid phases in stable stratification. So you have 2 liquid metals, one at the top and one at the bottom. And in between, so you have an electrolyte. And the ions from the top layer can go through the electrolyte and form an alloy in case of discharge. And then the advantages of these liquid metal batteries are for storage are that the 3 liquid phases are in stable stratification because you have different densities of each layer. You can have high current densities. There is nearly no erosion, and the lifetime is increased, and hopefully you can use cheap materials, and also you want to scale them towards large devices. But you also have some defects, some drawbacks. First, you can't transport them, so you cannot transport them. You need to heat all the metals such that they are liquids. You can get low cell voltage. And because you have some flows, these batteries are prone to instabilities that can, in fact, if the flow is too intense, you can get contact between the 2 liquid phases here, and then you will have short circuits. And also during fast discharge, what you can get some for which the ions from the top layer will alloy with the bottom layer with the component of the bottom layer. You can in fact you can see appearing a buoyant layer rich of the ions A, and so that may form an intermetallic phases in alloy during fast discharge. And in this case, you would like to have some flows, in fact, because it will decrease battery efficiency. And you need mixings. So sometimes you would like to have not too strong flows, but you want to have some flows in the bottom layer in order to homogenize this layer here. Yes. And then what is the outline of my talk? So I will first introduce the first study we've made about the electrovortex flow, which was mainly a poloidal flow. And then I will couple this flow. So it was an hydrodynamic study mainly. And then I will couple this electrovortex flow with buoyancy. So I will introduce, in fact, the fraction of the ion coming in the bottom layer. And then at the third part of my talk will study, in fact, the swirling electrovortex flow. And so first of all, I will introduce the electrovortex flow. So I will remind what is the Scherklif's mechanism. I will present the dimensionless equation that I will be integrate numerically, and we'll discuss the results for different settings. And then I will show some similitude laws, and I will conclude on this part for what I call the polyidal electrovortex flow. And so what is the source of this flow? In fact, the source of this flow is a deviation of the current due to the smaller current collector, and that gives rise to a rotational Lorentz force. So as a schematic here, you see that I will consider, in fact, liquid metal batteries which are in a cylindrical cavities here. And you see that you have some current collectors for which the radius of the wires, in fact, at the top and the bottom, the radius of the wire is smaller than the radius of the cell. And so in this case, you see that the current feed lines which are shown here in red, they are in fact deviated. And then in this case, we will see that it will create some forces which will push the flow, so that there will be an upward jet, for example, in the bottom part, and a downward jet in the above part, in the top part. And so these green streamlines correspond to the motion. And here on the right part, you see a numerical simulation for a symmetric battery, for which you see that the velocity is going up in the bottom part and down in the top part. And so in fact, the mechanism is described here. So imagine that you have a feeding line which has a very small radius, and then the current is arriving in a large bath, metallic bath. And so in this case, what we have is that the locus current GZ along this z-axis, vertical axis, we create an azimuthal magnetic field, which is represented here in blue. And so you have an azimuthal B theta, which is created. But due to the fact that the current lines can go on the side, you will have a radial component for the current density, GR. And so therefore you can have a Lorentz force. You will have a Lorentz force which is given by GR cross product with B theta, and that gives you a rotational force in the meridian plane, and which will give birth of the upward jet in this direction. And so in this case, you have a motion which is created, but it is created in a meridian plane, which is that this kind of motion is called the poloidal motion. Okay, and then so what we'll first study, the first configuration I will study, I will focus on the bottom layer. And so I'm using a code which is written in cylindrical coordinates. So all mainly the pictures I will be showing, the figure I will be showing, will correspond to a meridian plane, for which on the left side you will have the axis, and then you have the fluid here, and below you have the wire with this subscript W for the wire. All right, and so you have a current which go inside this wire, and which spread in the fluid. And then so we focus on that, and we use some dimensionless equations which are written here. So in the fluid, you have the magnitude hydrodynamics equations, for which you have U the velocity, P the pressure, and B the magnetic field. And here so that is a Navier-Stokes equation with the Lorentz force here on the right. And then for B, you have the induction equation, the magnetic induction equation in the fluid. And for the wire, you have no velocity, of course, but you need to integrate the magnetic field inside the wire. And so I'm using these units here, just like Miller or in the Boyarevich book. And so the control parameters in this case are two. They are the S parameter that I will call the EVF parameter. And so you see that it depends on the current density G squared. You have also the magnetic Prandtl number, which is equal to the conductivity of the fluid, the magnetic permeability of the vacuum, and the viscosity, the kinematic viscosity of the fluid. And in fact, I will prescribe the ratio between the conductivity of the wire divided by the conductivity of the fluid. And so if we integrate that, so we will fix a value of S, and we will fix a value of the magnetic Prandtl number, and we integrate the electrovortex flow in a single layer, first with only axisymmetric, in an axisymmetric numerical simulations. And so what you see here is different plot of this meridian plane. And on the left, you see that it is the velocity, the amplitude of the flow. And so you see it is a maximum along the axis, and it follows this upward jet as expected, and then it forms in fact an axisymmetric torus. And if you look to the current streamlines, so you see that they are spread here. And if you look to the J cross B, which will be the Lorentz force, you see that the Lorentz force is purely a meridian, and it will push, in fact, the fluid from the side toward the axis. And in fact, in this Lorentz force, you can split the Lorentz force between two parts. One part, which is a gradient, so it is an irrotational part, but you have a rotational part, which is the active part of the force, in fact, which is represented here, and which in fact pushes the fluid from the side toward the axis. Okay, and so we see that the electrovortex flow creates poloidal flow as expected, and in this case, it forms an axisymmetric torus for small s. And among the force, only this term drives the EVF. And the maximum speed Umax is for small s along the OZ axis here. And we will see that the maximum velocity varies with s. And so we are interested, in fact, in the scaling laws of this maximum velocity. So in fact, the maximum velocity corresponds to Reynolds number in our units. And so what I'm plotting here is a log-log plot for which I'm plotting the Reynolds number as a function of s. And you see that at small s, Reynolds number varies like s. But when you increase s, you will see that the Reynolds number varies like square root of s. And here I've varied the magnetic Prandtl number, right? And usually for liquid metal, you have 10 to the minus 6, and you have a better scaling like square root of s. And we can understand these scalings just looking for the force, a balance of a force, and the driving force, as we've seen, is the Lorentz force, and especially this term here, which scale like s. And if you first consider small s, in fact, you will have a balance between low intensity flows, meaning the Stokes flows. And so you will have a balance between the viscous term and the force and the Lorentz force. And that gives you that the Reynolds number should scale like s, for small intensity of flow. But for high intensity flows, in this case, you have a balance between the inertial term and the force. And that gives you, in this case, that the Reynolds number should scale like the square root of s. And these scaling were predicted. You can find the prediction in Boyarevich and collaborators' book for Prandtl number is equal to 0. And we can find that in the case for which the radius of the wire divided by the radius of the cylinder is O.2, you have such coefficient, and it was nearly what we found. And we see that in the scaling laws for small s, we have no dependency with respect to Prandtl number, but we have a small dependency here for large s. But anyway, what we see is that we have a transition for s around 5,000 between these two scaling laws. And so if you look to what happens for the flow, in fact, when you increase the s number, so increasing the current density, so what we see is that small s, we have one torus which is symmetrical from top to bottom. But when you increase s, what you see is that there is an appearance of a radial jet. So you have the upward jet, but also a radial jet, and a new corner vortex here. Okay, and then what we can say is that there is a transition between s is equal to 10 to the minus 4 and s is equal to 10 to the minus 5 between one toroidal vortex, one torus only, to two vortices, two tori in axisymmetric setting in the same range of the change of scalings. But what we ask also to ourselves is it a route to 3D effects? And the answer is yes. So what we perform, what I'm showing here is 3D simulations for which I've looked, for example, for large S behavior. What I'm plotting here as a function of time is the kinetic energy. And what you see is that at small time, in fact, at small time, the total kinetic energy is only axisymmetric. And here is a plot of what you get for the streamlines at the small time. So you see that it is all axisymmetric, and so you have a nice torus. But when you wait long enough, what you see is that the total kinetic energy is greater than the axisymmetric energy. So you have a toroidal, in fact, you have a toroidal kinetic energy arising, which is proportional to the azimuthal velocity squared. And that is the kind of streamlines that we get at this large time. And you see that it is no more axisymmetric. So you have some 3D effects. And then, in fact, we find that the bifurcation from axis to 3D is appearing for this value of S. For S greater than 7, 10 to the 4, you have 3D effects. And you have also this breaking of axisymmetry. But anyway, if you measure the non-axisymmetry energy ratio given by the difference between the total kinetic energy and the axisymmetric energy divided by the total kinetic energy, in fact, for the largest S that I've performed, that I've run, it is less than 13%. So what we decided is that we neglect the 3D effects and we use only axisymmetric computation for studying multiple layers, because we want to study liquid metal batteries. So what I am considering is magnesium antimony liquid metal batteries. So I'm using such geometry, which is symmetric from bottom to top. And so the fluid 1 is magnesium, fluid 2 is electrolyte, and the fluid 3 is antimony. And then we have copper wire. And we will only perform some, I will only perform some numerical simulation for a current which is greater than 100 amp. So in this case, we're in the high S regime and in both electrodes, meaning that the Reynolds number should scale like the square root of S, and that give you that the maximum velocity in each fluid part, liquid metal part, the maximum velocity should scale like that, meaning that it scales like the current divided by square root of the density of each fluid. And so because we have rho 1, which is smaller than rho 3, so we expect that to get a stronger flow in the fluid at the top electrode. And that is what I will show you. And so I will show a series of runs from DNS with a fixed geometry for the liquid metal battery as is given here. Okay, so what do we get? So I'm fixing, for example, the current at 200 amps. And then what we see here is not at time equals 0, just above 0. And so we see that we have a jet, which is very intense in the top liquid, in the top layer, as expected. But you have also a jet, which will be upward in the bottom layer. So downward here, upward there. So, and then you see that you have a radial jet also. And you will see that these jets, in fact, will deform, in fact, the interface. And here the interface between the fluid 1 and the electrolyte is really deformed, while the bottom interface between the electrolyte and the fluid 3 is nearly does not move. Okay, so let's look what happens. So you see here, I hope you see the movie. And so you see that the jet, in fact, will push the fluid, and the fluid will recirculate along the, in fact, following the walls, in fact, and will create some toroidal torus at the top and a less strong torus at the bottom. Okay. And at large time, in fact, in the asymptotic regime, what we get is that we have more and more small small length scale here, but you still have this recirculation, which is intense in the top layer and less intense in the bottom layer. All right. So what I show here is exactly the same run, but I'm plotting as a function of time the kinetic energy, and so you see it increases it's increasing for quite a long time, but then after at the end we reach an asymptotic regime. And so we see that that was at a small time. We see that we have these two jets which are appearing, and then at large time, in fact, you have this recirculation which is more intense in the top layer. And if we look at the value of the Reynolds number at the end of this run, we have Reynolds number which is kind of a turbulence, small, slightly turbulent. But what I want to stress is that during time evolution, you see that the top interface is deformed. And so we have measured, in fact, the maximum deformation that I call eta max, that will give us, in fact, let's say the thickness, the smallest thickness between the two interfaces here. And so I've performed different runs for different value of the current, and I've measured the maximum velocity and also the maximum deformation. All right. And so what we can understand, in fact, the variation of Umax with the current and eta max with the current also using a physical argument. So what we say is that we said that there is an energy balance for interface deformation between kinetic energy and potential gravity energy. So in fact, what we say that the kinetic energy is balanced, in fact, the potential energy, which give me for the top layer, which is ρ1, that the kinetic energy is of the same order than the potential gravity energy, which is given by this formula. And so equating the two, I can find that eta max is given by that, okay? But now I know that the Reynolds number scale as square root of S in this case, because we have a large current and a large S. And so that gives me that Umax should scale like that as before, but here is Umax in the top layer. And if I inject Umax in this formula, what I get is that I get that eta max should scale like I squared multiplied by some prefactors here. And so that's why here eta max varies like a parabola here in a range. And we see that as soon as eta max is of the same order of the thickness at time equals 0, therefore we will have a pinch. Okay. And we've seen here also that Umax vary like the current at power 1. So that's why we have a straight line here. We can thus define a Richardson number using this eta max, saying that in fact we will have something happening when the Richardson number is of order 1. Okay. So now what I want to do is to use this simulation and extend this result to other geometries using similitude laws and not performing any more DNS. So what I will do is that I will use my cases before that I call reference case, and then I will use different similitude laws. So what I'm doing is that I've performed some computation with this geometry, and now I will zoom, in fact, the geometry, but keeping the same ratio for the radius of the wire divided by the radius of the cell, which is this extension here, and the same aspect ratio for the total height divided by the radius. All right? And then I'm saying that there are some similitude laws, meaning that I will be using, I'm imposing that the same current going through the same, the zoomed liquid metal battery. There will have a similitude law for the Reynolds number, meaning that I'm using the same diffusive speed. And also I will use a similitude law for the Richardson number, meaning that I'm using the same energy balance. And so in this case, I have some simple law of transformation between the reference case scale case and the case I want to generalize with. And then what I'm showing here is three different scenarios, meaning for different J, different current density. What we see is that, so you have J is 1 kiloamps per meter squared till J is equal to 10 kiloamps per meter squared. And so I have Umax as a function of the radius. And so you see that I can vary the radius between, let's say, 5 centimeter till 50 centimeter. Then I have the law for Umax, and I have also the law for the maximum deformation for these three different scenarios. And you see that you have different zone here. And so the zone, in fact, correspond to the typical thickness for electrolytes. So suppose that you said that you want to use a liquid metal battery with a typical thickness for the electrolyte between 1 and 5 millimeters. And so what we can say is that for the scenario for which you have a current density of 1 coulombs per meter squared, you see that for any radius here, you will have the LMB will be safe because the deformation will be smaller. The maximum deformation will be smaller than the typical thickness for the electrolyte. But for the other scenario, the largest current density, we can say that this LMB will be rather unsafe because, in fact, for small radius, it's already in the dangerous region. All right. So I can conclude this first part saying that there is a good agreement with well-known scaling laws for single fluid in case of axisymmetric setting. We have identified a transition between small and large S regime related to the formation of another vortex. So we have two vortices. And the azimuthal mode M equals 0, the axisymmetric mode dominates the dynamics. And so therefore, we have computed multi-layer system only in an axisymmetric settings. And so we have found the maximum velocity in the top electrode for symmetric copper wise. And using the scaling laws, we could identify safe and unsafe region. And it seems that EVF could be important for stability of the LMBs, but we wanted to see if it could be important for the mixing capacities, all right, in the bottom layer. And so that is what I will show next. So now I will be using electrovortex flow, but also buoyancy in liquid metal batteries. And in fact, I will focus on the bottom layer, for which I will have this electrovortex flow, plus I will have a flux of lithium ions. So I'm using a LMB, which is lithium and lead. And then so I will have an incoming flux in case of discharge and an outgoing flux in case of charge. All right. And so in this case, the two important parameters are the S number as before, which is let's say the EVF parameter, but I have also a flux of ions, which is given by this formula. And so there's a question? No? And so what are the new equations in this case? We have a mass concentration. I will consider the mass concentration of lithium in the bottom layer, rho Li, and I will integrate this equation with a binary diffusion coefficient here. And in fact, I will translate all the result in a molar fraction XLE, which is given by this formula. Okay, so I will be interested in the molar fraction of lithium in the bottom layer. And I'm still integrating velocity and magnetic fields, which are given by these equations. So as before, we have the Navier-Stokes equation with the Lorentz force plus a Boussinesq term, which is due to the fact that the mass concentration of lithium is varying in time. All right, and so what do we get? In case of discharge, so in case of discharge, you have lithium ions coming from the top layer to the bottom layer, and I'm only representing here the bottom layer, and in the middle, you have the axis here. And so what you see at short time is that you see that you have the electrovortex flow. So the streamlines are represented here, and the color correspond to the field of molar fraction of lithium. Okay, and the molar fraction, what you see is that during time it increases because you feed more and more lithium in the bottom layer during discharge. And what you see is that you have a diffusive solution for the molar fraction, and the velocity is nearly nothing. At the end, the electrovortex flow is totally disappears. And in fact, we can measure the inhomogeneity of this in this bottom layer with the difference between the maximum and the minimum molar fraction. And what I'm plotting here is this inhomogeneity in XLI during time for different current density. And in the case of the current density that I'm plotting here, which is -5 coulombs per meter squared, what we get is we get this dotted curve here, which in fact corresponds to the diffusion, to the diffusive solution, as if the electrovortex flow was not existed. And what we've shown here is that the electrovortex flow is totally crushed by the stratification. In fact, the solution just becomes the diffusive solution, and the EVF has no impact on mixing when the buoyancy is modeled, because the flow is not enough strong to pierce this stable layer here. All right, but now what happens in the case of charge, meaning that we remove now some lithium from the bottom layer. And so in this case, I'm presenting some numerical result for the J, which is 50 amps per meter squared. So, and an axisymmetric study. And so I'm showing here the axisymmetric velocity as a function of time. And so you see that you have different behavior for the velocity that can be related to what happens in the flow. So on the left, I'm showing the magnitude of the flow. On the right, I'm showing the molar fraction. And so this red arrows just is telling that we remove lithium from the bottom layer, from the alloy in the bottom layer. All right. And so what happens is that at short time, we have electrovortex flow. And so we get the velocity which corresponds to this electrovortex flow. But after a while, in fact, what you get is that because you remove lithium from this alloy, you get heavier alloy on top. And what you see is that you have, in fact, the heavier alloy will drop because it is heavier, and it will drop in the bottom layer, and it will form some plumes, and that corresponds to this phase for the velocity, which increase because of these plumes. And when the plumes reaches the bottom lead here, therefore there will have larger recirculation. And then, in fact, solitary convection will take over the electrovortex flow, and this convection corresponds to the second plateau in the value of the velocity. So that was with axisymmetric computation, but what happens in 3D? And in 3D, for the same current density, we see that we have this sharp increase of the axisymmetric velocity. You reach a plateau, which corresponds to the solitary convection. And then you have these kind of things with large recirculation and some plumes of heavier alloy. But then after a while, you have 3D effects which take place. And so you see that if you wait long enough, therefore you will have some 3D modes which appear, and you can see from the top view that you have a lot of small scales coming into play. All right. So in fact, in real life, it should be 3D. The charge will be 3D with buoyancy. But what about mixing? Because we wanted to mix this bottom layer. So back to the measure of the inhomogeneity during discharge and charge. So what we can say is that during discharge, when you consider the buoyancy, in fact, the solution correspond to the diffusive solution, and because the electrovortex flow is not strong enough to counter the stable stratification. And in case of charge, what we get is that the inhomogeneity is quite small, and therefore we are quite happy. But the mixing is not due to the electrovortex flow; it is due to solitary convection, and in this case, the EVF is totally negligible. Right? So now, what we want to estimate is the different discharge scenarios and the mixing. And so, as I said, due to solitary buoyancy, the EVF is not strong enough to penetrate the stable light layer, and the molar fraction of lithium is controlled by diffusion. But how intense a fluid flow should be to be able to counteract the stabilizing buoyancy? So we have estimated two characteristic velocity scales using energy balance. First, we have estimated the minimal flow which could pierce through the stratified layer near the interface, and we found that this UP for piercing is given by this formula, for which you have the beta, which is a solitary expansion coefficient. And we can also estimate a minimal flow for efficient mixing, saying that we want that the fluid transport the flow should transport the fluids all around the alloy layer. And so in this case, we have another velocity, which is given by UM for mixing, which is given by this formula. And the different scenarios will be that if the velocity of the flow, if the intensity of the flow that you get is smaller than UP, therefore you will have no influence on mixing. If you have the velocity, the intensity of the flow, which is greater than UM, then therefore you will have efficient mixing, and in between the flow will have only a moderate influence for a finite amount of time. Any question? No?
No, just someone joined the seminar.
Sorry?
Someone just joined the seminar.
Ah, okay. So here's a conclusion of the second part, is that during discharge, the solitary buoyancy just blocks the dynamic mixing, and the EVF is not able to mix the alloy due to this lighter layer on the top. And during charge, in fact, the buoyancy creates solitary convection, which mixes the alloy, and in this case, this EVF is negligible. But now the question is that, so therefore mixing is active during charge phase of the liquid metal battery, but what about the discharge? We want to generate a strong flow to enhance mixing during the discharge phase. And so for that, we will study the swirling electrovortex flow. So what is the swirling electrovortex flow? We will focus therefore on the discharge, and still we will focus on the bottom layer. And we have the background magnetic field BZ, right? And so in this case, let's look to the scheme here. You see that if you cross product the radial component of the current with the BZ, therefore you will have an azimuthal force that will appear, and this force will be localized near the connection between the wire and the cell and the layer here. And so this azimuthal force will act just like a bender. All right. And so what we do is that we compute this. We use the same equation and geometry as before, but now I recall them here, and now we have this new BZ. Okay. And so what I will perform is first an axisymmetric study. So I will prescribe the current density, which is -5 kiloamps per meter squared, and I will vary the BZ. Okay. And so the results are shown here. So what I'm plotting is during time, the time evolution, therefore, of the surface average of the molar fraction. And so for different BZ. So what I'm plotting in black are limit solution. The solution in black at the top is a pure diffusion solution, and at the bottom it corresponds to the perfect mix. Okay? And so what we see is that when we increase the magnetic field from 1 millitesla to 10 millitesla, what we see is that we have the stronger BZ, the more mix you have, because you see that XLES, surface average of XLE, therefore is nearly following the perfect mix solution. And so what happens when you look at the molar fraction? So here I'm plotting. So in the middle you have the axis, and so you see how is distributed the molar fraction. And so you see that in fact when you increase the BZ, you have more and more mix, meaning that the XLE is nearly is less than 19%. All right, nearly the same value as before. So you have a perfect mix in this case. And this mixing, in fact, is enhanced. The mixing is enhanced, we could say, when BZ is greater than 2.5 millitesla. Okay? And now I will show you some movies. So here I'm plotting the slice, and you see here the cylinder. And first I'm showing the molar fraction. And so at the beginning, in fact, you will see that the molar fraction will form kind of Kelvin-Helmholtz here rolls, and then you will have some mix. The mixing will be acting and will just mix all the molar fraction all around, okay? And what happens for the velocity? So for the velocity, we have a blender which is really efficient at the bottom that will in fact create a jet which will be downwards, and then we will see that we will have kind of plumes of the velocity. So that is a magnitude of the velocity, and you see that you have a conical form here, and you have some shear instability which forms some Kelvin-Helmholtz rows, and then the velocity is mainly is in fact always important near the source of the motion. All right, and then what happened in 3D? So I'm taking the same parameters, and now I'm integrating in 3D. All right. So what we will see is that at the beginning, the molar fraction is nearly axis symmetric, but after a while, it's about above 15 seconds around there, you see that you start to have some 3D pattern on the top, and you also see that it is no more symmetric left-right, from left to right on this plot here. So that is the molar fraction in 3D. And here from the top now, let's look from the top. So we see at the beginning it's nearly axis symmetric, but if you wait long enough, you will see some modes appearing near the middle and all over after. And if you wait, you see some spirals appearing after 15 seconds. Okay, so we need some time to see something. And what about the flow? So I'm just plotting here a movie for the flow after 15 seconds. And so you see that after 15 seconds there, you have still, all the flow is 3D. You have a lot of small scales all around, and the magnitude, the intense flow is near, in fact, near the central region of the layer. All right. Then we want to compare this asymmetric and 3D study. So what I'm showing here is around 20 seconds, the 3D molar fraction, the axisymmetric molar fraction, and here that is the magnitude of the flow in 3D and the magnitude of the flow in axisymmetric setting. So what I want to stress is that the 3D DNS is very demanding, because if you look at the Reynolds number, it is about 14,000. But the worst thing is coming from the Pecla number, which is given by this formula and which is greater than 10 to the 5. And then therefore they explained that I really need to have very small time step, and I could only use get a maximum computation of about 18 seconds, because after the code just explodes. All right, but anyway, we can compare the surface average of the molar fraction as a function of time. So in green, that will be the axisymmetric one, and in red, the 3D one. And you see that we have an intense mixing in both cases, even if it seems to be slightly less efficient in 3D. And for the velocity, what I'm plotting here as a function of time and logarithmic scale here for the velocity, we see that the axisymmetric part for the root mean square velocity from 3D is almost identical to the pure axis one, because the red and the green is nearly the same, and you need to wait till about 12 seconds to see some 3D velocity playing a role here. So we think that we have a good mixing estimate from axisymmetric simulation only. All right, so I will be using only axisymmetric runs now to perform some parametric studies. Or I fix J and I vary BZ, or I fix BZ and I vary J, the current density. And I get a scaling law over 3 decades. And so what I'm plotting here is in log-log scale. I'm plotting the toroidal velocity average in time when the flow is fluctuating. And so you see that you have a nice scaling, which is given, in fact, which is given by this formula, for which the velocity varies like the current density multiplied by Bz to the power 2/3. And you have some points which are not aligned with the scaling law, because in fact, in this case, there is a non-negligible induced currents that break the swelling EVF. But I will mainly use this scaling anyway. And I will take, in fact, the value of the velocity, the maximum velocity for these different runs, okay? When I have 1 millitesla, there is nearly no mixing, but for BZ above 2.5 millitesla, I have mixing, right? I'm measuring the maximum velocity, and I'm plotting this maximum velocity here as a function of this parameter, of these scaling laws. And so here, for 1 millitesla, I have no mixing. For the other BZ, which are greater, I have mixing, all right? And so I can use a fit here to find what is the value of maximum velocity when I have mixing, okay? So I'm fitting along this gray line, and that gives me this formula, that gives me, in fact, this constant, which will depend on the setup geometry. And now I want to compare this maximum velocity with the U piercing and U mixing that I've defined before for this current density that I'm studying. So in this case, I'm using the formula with all the constants that I know. And what I found is that the U piercing is about 6 millimeters per second, which corresponds to this line here in orange. And U mixing is about 4 centimeters per second, which correspond to this pink lines here, right? And so what I can say is that it seems that the mixing criterion should be that the maximum velocity should be greater than U mixing at transition between no mixing and mixing cases. And so I can generalize in this case. And so I'm plotting here the validation of the mixing criterion in a graph with J on the horizontal line and BZ on the vertical line. And so we see that in the gray zone here, you have no mixing, and above the gray zone, you can get mixing. So you can perform different experiments, and you can get this kind of estimate. And so now, if I want to discuss the mixing criteria in terms of BZ, so I remind you the 3 different regimes of mixing. And I'm using the aspect ratio H/R, which is given, and the scaling law that I found for the maximum velocity. And then if I replace this formula in U piercing and U mixing, I found that for BZ smaller than this formula, there I will have no mixing, but for BZ greater than this formula, I will have efficient mixing. And if I'm using the parameter I've used in the DNS. Therefore, I found that the base edge should be greater than 1.2 millitesla for this current density of -5 coulombs per meter squared to get efficient mixing. And then it is consistent with our results. So if you want more details, you can look at the last paper on this swirling AVF. And so that is my, my final conclusion for the liquid metal battery with respect to mixing in the bottom layer, for which you have the alloy. And so the poloidal electrovortex flow apparently was a good idea for mixing, but what we found is that when you add buoyancy, in fact, that is a solitary buoyancy, that is a key player, because during discharge, it blocks dynamic mixing and the electrovortex flow is not able to mix the alloy, the electrovortex flow, which is purely poloidal. And during charge, it is a solitary buoyancy, which creates solitary convection, which mixes the alloy. And in this case, the flow due to the electrovortex flow is negligible. But what we have found is that the swirling LVF, for which you have an azimuthal velocity, is efficient during discharge to enhance mixing if the flow intensity is greater than this UM. All right, so I thank you for your attention, and I will be happy to answer your questions, and I will switch on my my camera.
Great. Excellent. Thank you very much. So, yeah, amazing results, as Ms. Mora said. Yeah, we have enough time for questions. Please feel free to ask.
It seems that I can't find my camera. Wait a minute. Yes.
Yeah, we can see you now.
All right. Okay.
Excellent. So,
can't see you because I have my slides. So maybe I should. I don't know. Maybe if you have some question, I will come back to my presentation. I don't know.
Exactly. So yeah, we have time for questions. Please go ahead with them.
Hi, I'll ask a question. First of all, thanks for the excellent talk, Carolyn, and thanks for inviting me and the rest of the Doug Kelly's group, Alberto, for this seminar. I had one question about when you have the case of solidal convection. So that's during charge, I think, right? So you have convective mixing from lithium being extracted from the top.
Yes.
Layer. So in that case, you also should theoretically have electrovortex flow happening at the same time. Is it that is there significant effect at all from electrovortex flow, or would you say that all of the velocities and all the mixing is essentially just dependent on the convection?
Do you see my slide here?
Yeah.
Or no? Yeah. So you can see them. So in fact, yes, you at the beginning you see the electrovortex flow here, right? On the left, you see my I don't know if you see my arrow, my mouse. Yes, you see, right. And so in fact, you see that at the beginning you have the electrovortex flow as expected, but the velocity is very small because it is you see 10 to the -7 meter squared meter per second, and so it's really small. Yeah. And then after a while, because you have heavier alloy on the top, therefore the heavier alloy will just drop, and then that is this drop which will in fact create this flow, and which is really which in fact explain why you have this increase, which is an exponential increase of the velocity until this plume, the central plume here, reaches the bottom of your layer and will in fact organize the flow on a large scale flow. Okay. And I think that Paolo Personetas and Norbert and collaborators already shown that. Okay, it was known already that the solitary convection, in fact, in case of charge, is the main player, and the AVF just exists, but you can only see it at the beginning.
And you don't think that it would? It's so much smaller, so it's probably not going to have any. You know, it won't organize the convection in any way or anything like that.
I don't think so. I don't think so.
That seems to make
because what we should do is in fact to compare, to look at the value that you can reach with only the electrovortex flow. Okay. And it's never so large. I mean, in this purely toroidal electrovortex flow. So that's right that in this part, I'm only using a Reynolds number, but with I don't remember if I have something that I'm measuring in meter per square. And yes, charge here, it's very small in this case, but that's right. That what happens if I vary the current density? But I'm sure that it is always small, with respect to the velocity that you gain with the solitary convection.
Thank you.
You're welcome.
There is one question on the chat from Gerrit. It says, thank you for the great talk, Caroline. I have one question. Do you know if the Earth magnetic field alone can be strong enough to guarantee mixing in future large-scale batteries by swirling electrovortex flows?
Ooh, I didn't really understand what you said, because my mic.
Yeah. Do you know if the Earth magnetic field alone can be strong enough to guarantee mixing in future large-scale batteries by swirling electrovortex flows?
If I know that, I mean, what I guess it should be only small, as I've shown. Sorry for that. As I've shown in our case. So of course, in our case, the radius was only 4 centimeter. And so I guess that what Gerrit is asking is what is the value? So what we should do is in fact take this formula here, all right? And so if you know what is the geometry that you want, meaning what is the radius that you want to with which you want to construct your battery, what is the aspect ratio, the small h, which is h over r of the bottom layer. All right, and you know all these different quantity, the molar mass of the lithium, the solitary expansion, you know all these constants here, and you know the viscosity of your alloy, and you know all that. Therefore, you will have the value of Bz that you need to get in order to have efficient mixing. Is it the right answer? I'm not sure.
He was worried about the magnetic field, the Earth magnetic field, the effect.
Sorry, the Earth's magnetic field?
Yes.
No. No, the Earth's magnetic field, as you see, the Earth's magnetic field, we know that it is what? It is about 1 Gauss 10 to the minus 4 Tesla, so 0.1 millitesla.
Yes.
So for me, shouldn't be so important.
Okay.
Because we need it shouldn't be so important. I don't think so. But maybe the right thing would be, imagine that you have Bz, which is 0.1 millitesla, right? And I want it to be equal to that. And I'm looking for R such that I guess R and the H such that I have this equality between the two. And so that will give us the R and maybe the H.
Okay.
Maybe
Yes.
take the thing and we need to find some to pick up some values for the different for the current density, for example, also.
Sure. He just answered. He have no micro today. Yes, I think if R is very large, BC of the Earth could be sufficient for this condition. Yes, it seems that he's agree with you.
Yeah.
I have one question. Your dissipation is taken into account in all your simulations, or it is not? Joule heating.
Sorry, which the Joule heating? No, I'm not taking that into account. You mean that would be, as you see here, I'm not using the Joule heating as a source term in the equation. I'm looking for the equation here, right? So the equation I'm using written there. So you have this mass concentration evolution equation for the evolution of the mass concentration of lithium. What is very difficult is due to the small value of this binary diffusion coefficient that we took very small, right? And for the momentum equation, so we have the Lorentz force and we have the Boussinesq term. And for the magnetic field, we don't have any Joule heating into account. No. I mean, we don't have Joule heating. Would be yes, for that would be Joule heating if you would like to, in fact, to couple to the temperature field, right? Yes, yeah, but I think that if you look to the order of magnitude of the convection, it's in fact in this case it will in fact be dominant in the electrolyte layer, right? And so I think that Zikhanov and collaborators studied that, and others also, that you have a Joule heating mainly in the electrolyte layer that create a hot temperature in the electrolyte, and so for the bottom layer you have a hot temperature at the top, but could be cold temperature at the bottom, and so it will be a stable kind of it's the inverse of Rayleigh-Bénard. So it is a stable temperature profile, right?
Right.
So I don't think that Joule heating is so important. We should look. That's right, but I don't think it is a source of motion in this case.
Are there any more questions? Maybe.
Yeah, I have a question, please.
Yes, have you?
Yes.
Okay. Caroline, thank you very much for your excellent talk. It was really interesting and clear.
Thank you.
Well, I would like to go to this problem when you introduced the axial magnetic field, and
yes.
So the swirling flow that is produced is mostly concentrated on the bottom part, but you explained something that I probably I didn't understand completely. That finally you had a kind of instability that produces the mixing in the whole region, because the swirling flow is mainly in this bottom region, but finally you get a good mixing if the magnetic field is high enough. So
yes,
could you go to this explanation again, please? Just to
so as you said, you're totally right that in fact the force is really localized to the where the wire is connected to the fluid, right? So you have a localization of the force, but it is as if you had a blender, right? And so the blender will create Ekman recirculation, right? And so the Ekman recirculation, in fact, will create a downward jet, and the fluid, of course, has to recirculate on I don't know if you see my mouse. Yes, you see. And then so you have Ekman pumping, in fact, and so you have a downward jet, and so the downward jet will go this direction, and then there will have a recirculation, and so therefore you will have kind like a von Karman half von Karman flow, right? So you have Ekman pumping and recirculation, and it is very efficient. In fact, just like a blender. If you want to make a smoothie, you will do that, right? And you will see that you will have a very efficient mixing, and that is what I was showing. I think the best is when we look to the movie. I don't know if you can see the movie.
Yes.
Yes, so the movie for the flow, for the velocity is in fact large where you have the force, which is large, but then after it's going all around and it is always still very active, as you see, and you have a lot of recirculation all over, and then that mixing pretty efficiently the sorry, I can't go to the to this guy here. And so you see that you have this downward jet that entrain that take the lithium with, and then it will the lithium will just flow all around and just will be mixed. It is totally different from the diffusive solution, for which you will get, you see, as I've shown before, the diffusive one, meaning with the other electrovortex flow, was this this view, for which you have the lithium coming in, and it just stay on the top, because the poloidal electrovortex flow is not strong enough, and so therefore you have no mixing here. You have all the layers which are just coming on the top, and they are stable by stratification, because they are less heavy than the the top part is lighter than the bottom part.
Okay, yes, and the difference between the charge and discharge is noticeable. I mean, once you introduce this, so once you introduce the actual magnetic field, so you have the same mechanism, but just a difference between the charge and discharge in the mixing, right?
What I said is that first in the part with electrovortex flow and buoyancy, when we have the electrovortex flow, which is only poloidal, what you see is that you have something which is totally different between discharge and charge, as you said, meaning discharge EVF is not strong enough, and it is not efficient for mixing. While during charge, in fact, it is not EVF which is a key player, but it will be the solutal convection, because in case of charge, because you are removing some light lithium ions, in this case you have a AV alloy on top, and so because you have AV material on the top, the AV material will fall down and will create, in fact, recirculation due to the solutal convection. Okay, so in the case of this electrovortex flow, which is only poloidal, you have something which is totally asymmetric between charge and discharge. That's right. But then after we decided to focus on the discharge case, and because we wanted mixing in this case, right? And so we decided to add a vertical magnetic field, because in this case, the vertical magnetic field will give you a new force, which is an azimuthal force, and that's why we call it the swirling electrovortex flow. In this case, not only you have this this motion, which is poloidal UR and UZ, but you also have U theta, and in fact, the U theta is a blender part, is very efficient. And so you see that you have something which is totally different. So I pick up exactly the same geometry as before. I pick up the same current density as before. And if I after just add a small magnetic field BZ, you see that you have no more these layers on the top, but you have all the let's say all the lithium is mixed. Thanks to this blender force.
Yeah. Okay. Okay. Thank you very much, Caroline. Thank you.
You're welcome.
Great. Thank you. So, are there more questions, maybe?
I would have a small one, if I may.
Yes, please go ahead, Tom.
And it's again a thanks first of all for the nice talk, Caroline. These very high resolved calculations. They are really fascinating. It's again the slide
you.
that we have seen very often today and that Jonathan started to discuss with you. I think it's slide 19, the axisymmetric calculations.
19, let's see, this one, right?
Right.
Sorry. Yes, this one.
I wonder why the plume starts exactly in the middle. So there is the electrovortex flow that's going upwards, and
That's
I
right.
would expect to drive the highly concentrated layer a little bit out of the middle, but it starts in the middle. That's something I'm puzzling with at the moment. Do you have an answer for this? And a second short question would be, can you give us a Rayleigh number for the convection?
Rayleigh number for the convection? I have no idea.
Okay.
I should think about that Rayleigh number, because you want the Rayleigh number due to the diffusive the Rayleigh the diffusive Rayleigh number, right?
The solutal Rayleigh number, just to get an idea how overcritical the flow is.
Yeah, in fact, we at the beginning we wanted to have this kind of numbers in mind, but in fact, for us it was not worth it. Why? Because it is totally unstable. There won't be any critical Rayleigh number, I guess, because as soon as you remove lithium. Right. So in this case, it's no worse for me. It's no worse to look at these kind of things because you don't have any threshold. As soon as you remove lithium, and even with a small j, as it is chosen here, as soon as you remove lithium here, you will get heavier alloy at the bottom, and so it should fall, right? So you so you don't have any instability. I mean, right? So that's why we were not interested in let's say estimating the Rayleigh number, the solutal Rayleigh number in this case, because there is nothing to compare with. And for you question as why the plumes in fact is faster on the axis. That's right. I have no idea. I wanted to in fact to study this kind of unique, let's say unique plume. That would be interesting to make a connection between these plumes and the plume from convection. But I don't know if it is really worth it, because in fact it is in this case axisymmetric, and all right, and maybe the axisymmetry will impose some symmetry, some let's say some let's say fictitious symmetry, right? Because I'm sure that in real life, in fact, you will have 3D perturbation just before to get these kind of things. And of course, when I'm showing here the 3D runs, we need to wait quite a long time before to get some 3D motions. But it is because we don't put any perturbation in the numerics. So that means that you see here, the slide before was still 90 seconds, sorry, and the velocity you reach in axisymmetric is about 1 millimeter per second, right, due to solutal convection. And then here we go, so we have here the 1 millimeter per second, all right, we here around 100 seconds, and then we had to wait quite a long time to get the 3D effect appearing through the 3D velocity. But we had to, after we stopped these runs because we were focusing on the axisymmetric setting. But I'm sure that if we put some perturbation right from the beginning, we won't have this central plume at the beginning, right? But for now, I don't know why in the axisymmetric case the plume, the largest plume, meaning the heavier alloy is right on the center.
Okay.
Right.
As for the Rayleigh number, I'm not sure that I completely agree, because it's more or less the exact counterpart of Rayleigh-Bénard, right? And
that's right.
If the diffusive transport of lithium would be fast enough, then you would have a diffusive mixing. So there should be a critical Rayleigh number also in the soluble case. But for sure, your Rayleigh number is far above the critical one. That's for sure.
Yeah, sure, maybe. Yeah, I should look to that, but for sure we didn't.
No, it's not critical.
I would say that you can kind of see the kind of famous Bénard like cellular shapes if you look at this top view that you have visible right now. And I suppose if
that's nice. That's nice. It looks like Marangoni, right?
Yeah,
it
yeah,
looks
yeah,
like, yeah. It looks like Marangoni. So that's why I was showing this top view, because I really like it. Because you see that it is very complex form, right? But
yeah.
that's right. I didn't. Maybe I should look at this soluble Rayleigh number, but I was not thinking on really determining any threshold on that. But,
yeah, I suppose what could happen is maybe if it were more supercritical, then you would get something like a large-scale circulation and it would not be organized this way or something like that. I don't know what it would be in an actual battery. I was just
that's
thinking
right.
of maybe some other way that Rayleigh number could be.
Good point. Yes. But for that, in fact, we need to have, real numbers. I mean, if you want, which kind of liquid metal batteries you want to study, and do you really get, I mean, all the physical properties in order to get these kind of parameters, at least the order of magnitude of these parameters. That would be nice. Yes, to discuss on that.
Okay. Any more questions from the audience, maybe? There are no more questions on the chat. I think if there are no more questions, we can conclude the seminar. We really would like to thank Professor Caroline Nore for this very nice talk. We were all very excited about her results. So thank you very much, Professor. Any comments from you?
Oh no, that was. I really appreciate that you invite me to give this talk, and that's right. That was a good opportunity to explain all what we've done on Electrovortex flow. But I would like to really thank Norbert Weber. He was the one who pushed us to study this kind of flow. And yes, it's always nice to collaborate with different people.
Great. Excellent. Well, thank you very much for attending the seminar today, and hopefully we will see you on the next seminar next month.
Sure.
Well,
thank you. Bye-bye. Have a nice day.